Thanks for the nice introduction. Hi, my name is Zheng Leong. I'm one of the authors of this work, which introduces a new way to kind of like do taint analysis. The objective of this work is to make taint tracking feasible for architectures both old and new, without the need for instruction semantics. So, taint analysis, since its introduction probably decades ago, has been a mainstay in computer security. It has a wide range of applications, from vulnerability detection to enforcing defenses. So taint analysis allows us to actually track information flow within a program for a particular variable. So how do we usually do this? So, okay. So how do we usually do this? The way that we typically do this is by setting the input of a program as tainted. And classically, people would actually write a bunch of rules to explain how the taint is propagated from the input to the output of a particular statement. So take, for example, this assignment statement. We would actually propagate the taint data, the taint metadata from map, from the source to the destination. So this is actually taint analysis for a normal source-based program. How do we do it for binaries? It's actually, sorry. It's actually, hello. Is this okay? Okay, great. So where was I? I'm sorry. Okay, so for taint analysis in binary, what we can do really is, it's similar to that of a source code. What we are doing is to, instead of having taint rules for statements, we instead have taint rules for instructions. So let's take a look at a concrete example and see how does this taint rule actually look like. I'm pretty sure most of you should be quite familiar with this. This is the logical AND instruction on the x86 ISA. So with this, the semantics for this instruction is rather simple. It takes the bitwise logical AND of the bitwise AND of these two operands. So let's take a look at how taint engines implement this particular taint rule. Some taint engines might just propagate the taint from the source to the destination. So in this case, the taint of EAX is kept. A more refined taint rule will actually consider implicit operands that this instruction has. So in this case, the taint is actually propagated to the status flag. And even more accurate modeling of the instruction would consider what we call input context sensitivity. What does this mean? So what it means is that, for example, if the second operand of this instruction is a 0, then the first operand actually does not have any influence at all on the output. And the right taint propagation rule is actually to clear off the taint in the output. So really, depending on the kind of like precision and understanding that the rule writer have, you can have different details of the rule. So why is writing a rule such a complicated affair? I mean, what we have on screen here is actually an excerpt on an exact rule for this AND instruction. It looks kind of complicated, so don't have to read it. The reason why it's so complicated really is that in the rule, we actually have to deal with all this input-dependent propagation. So like what I've mentioned previously. We also have to deal with the propagation of different sized operands. And finally, we also have to consider whether that particular architecture that we are coding for has certain quirks that the ISA designers put in for backwards compatibility. In this example, it's actually between 32-bit and 64-bit x86. So really, with all this problem, hello? Okay. So with all this problem, really, the question that we want to ask is, can we actually write these taint rules without using all this, without understanding all this complicated semantics? Well, the answer is actually yes, and this is one of the main contributions of our work. In our work, we actually propose using this new inductive approach to kind of like infer what a taint rule is. This particular approach uses something what we call a probe and observe method, in which we concretely test each instruction by providing the instruction and input and observing the output. We have also implemented this particular approach in our prototype tool called TAINT INDUCE, and as I will show in the evaluation, it does indeed produce useful tools for different architectures. So, in order for us to do this, we need to kind of like recast the way that we think about TAINT rules. I mean, for the past 10 or 15 years, when we talk about TAINT rules, what we'll think about is I will get the instruction semantics and convert it into a rule. Rather, in this work, we would kind of like recast this problem. We will define TAINT actually as a set of influence relations from the input to the output. In order for us to do this, we have to make certain assumptions. We made certain assumptions on the kind of like architectural structure. But these assumptions actually hold true for most von Neumann architectures. So the assumptions that we have is that we are able to read and modify the CPU, the values of the CPU register, and we are able to do the same for memory operands of an instruction. The influence is then defined as just a change in the input resulting in a change in the output. So I would kind of like to point out that actually this definition is different from all the influences that were being discussed in previous TAINT propagation or TAINT tracking papers. You might actually wonder if this definition or this representation of TAINT is sufficient for TAINT analysis. The answer is actually yes. We can actually map the traditional dependencies like direct, indirect, and implicit dependencies into our new problem setting. If you're interested in the details, you can actually refer to the paper. I'll just skip over for now. And in order to kind of like progress forward and compare our approach with existing TAINT engines, we have actually defined what this influence is mathematically. And using this new definition, we have come out on what soundness means and what completeness means. So to briefly touch on it, we say that a system is sound if it does not over-taint, and we say that a system is complete if it does not under-taint. So it's really, really, really hard to actually get TAINT rules that are both sound and complete. And in our work, we never claim that we generate rules that are both sound and complete. What we are really aiming for is to generate rules that are practical. And we'll see how we can actually do that. So the approach is rather straightforward under these new problem settings. What we'll do is there's a bunch of instructions which we are interested in. We'll take the instruction that we are interested in and generate observations for them. What is an observation, you might ask? An observation is simply just a tuple, that, an input-output pair, which can be generated by taking an initial input, executing it using a concrete black box, instruction black box of the CPU, and obtaining the output. With all these observations, we can then use our inference engine to infer a rule out of it. The rule that we are inferring is actually both sound and complete with respect to the observations that we had. Then you might be thinking, like, this rule is actually very restricted since we can only apply it on those input states that we have seen before. So we would actually like to generalize the rule to be able to apply it to input states which we have never seen before. And in the presentation, I will actually outline a very simple modification to the algorithm that allows us to do it. So let's take a look at exactly how do we do this particular inference in exact mode. We have the input-output state of a particular instruction. What I would like to do is actually I would like to flip one single bit in the input state because we are doing bit-level TAINT propagation. And after making this bit flip, I'll execute the new state and I'll observe what is the output. In this case, I've actually flipped the least significant bit of the register EBX, and I can actually observe a change in both the EBX and EAX register. This actually tells me that there's an influence between the EBX input and the EAX output. But do note that this influence is only valid for the particular initial state that we have seen before, because we are working in exact mode. And what we really want is in exact mode is that we want to have a set of input states that we have seen before. And what we say is that if the input state, if I've seen this input state before, then the influence is valid. So the way that we can do it is we can represent the input states in a truth table. And as we obtain more and more observations, we can add in new entries to this truth table. And when we are done with the observations, we'll set conservatively all unseen values to false. With that, actually, we basically have a condition guard that can guard our rule to enable us to apply this rule to just seen observations. We use a Boolean minimization algorithm to get a more succinct representation of this particular guard. So we don't have to have a disjunction of all the different input states that we have, which can be actually pretty big. So how do we actually make it generalized across to unseen values? We just need to make one very simple change. Instead of setting all unseen values to false, we will actually set it to don't cast. That means what we are saying is that, hey, the Boolean minimization algorithm, you can say that unseen values can either be true or false as long as you give me the most succinct condition you can find to separate these two sets. And in this particular example, the move example, what we have is actually the correct rule in which is a direct dependence between the EBX register and the EAX register. I would also like to point out this very interesting case, which the audience you might have in mind. How do we actually handle implicit dependencies, like conditions? We'll use a concrete example, the conditional move instruction. For the conditional move instruction, what we'll have is, during our observations, we actually observe two sets of different observations. One where EBX affects EAX, another one where EBX does not affect EAX. And from these two sets, we can actually form two sets of observed input states with this. How do we reconcile the fact that there's this mixed dependency here? Well, actually, we have already done that. The Boolean minimization actually finds this, the simplest, basically, line that can separate these two sets. And if we just run the particular truth table that we have, we set one partition to true and the other to false with a Boolean minimization routine. What we have is that we will get a condition where if CF is true and all other bits really doesn't matter, we will have EBX affects EBX influence EAX, otherwise there's no such influence. So in order to show how effective this approach is in the real world, we have evaluated our prototype implementation, TAINT INDUCE, on the coverage, the ability of it to detect real-world exploits, and we compare it with existing popular tools, TAINT engines. To evaluate the coverage, what we do is we'll obtain the rule for the instruction by training it using 100 random seeds, and we will test the rule with 1,000 random input. So we will say that the rule is sound, that means it doesn't overtaint, if for all 1,000 random inputs, for all the influence, we can have a witness for it. And what we have observed is that TAINT INDUCE never overtaint for 71% of the instructions across all the 4 tested architecture. And this is including instructions such as, including SIMD instructions and floating point instructions. Next, you might say that, oh, yeah, it doesn't overtaint, but it might undertaint so much that it's not useful in the real world. So in this case, we have selected 26 CVEs from real-world program. These CVEs cover a wide range of vulnerabilities, and the TAINT propagation policy that we chose is to track direct dependencies only. This is similar to other approaches, and the result that we have is that we are able to detect taint on 24 out of 26 of the exploit traces. For the remaining 2, the value of the taint source is actually indirectly derived from the source, and hence, based on our taint propagation policy, we do not track those. This actually tells us that the rules that are generated by TAINT INDUCE do not undertaint so much that it isn't useful in the practical sense. So let's take a look at how does TAINT INDUCE compare with existing TAINT engines, popular TAINT engines. For this, we actually took 3 TAINT engines, TEMU, Triton, and libdft, and compared against them. So for all the instructions that these TAINT engines support, we have identified that for more than 90% of the time, we actually propagate the rule in the same manner as this TAINT engine. And in times where there's a discrepancy, only 0.28% of the discrepancies are due to errors in the rule generated by TAINT INDUCE. For all these discrepancies, the reason is because TAINT INDUCE did not observe a particular influence relation from the observation set that we have. Do take note that all these engines just support a subset of the x86 instruction, and really, this is probably the first time we actually have a method for us to, in a not so painful way, obtain TAINT rules for architectures such as ARM and MIPS and so on. So with that, I would like kind of like to conclude by saying that in this particular work, we have basically provided an alternate view on how TAINT rules can be written, can be inferred from, and I truly believe that this can open up a new direction in trying to make TAINT tracking useful in the future. We have shown that this approach actually allows us to reduce the engineering effort needed to write these rules, and this improves the usability of TAINT. We have shown through our evaluation that TAINT INDUCE work well in practice and is comparable to existing TAINT engines. So with that, I thank you for your attention, and I'm open to questions. Thank you.
Okay, thanks a lot for your work. I have a question that basically, for given any architecture, there is some kind of the documentation that illustrates the information flow semantics of the each and every instructions.
Mm-hmm.
Why do we still need a TAINT INDUCE?
So for example, I'll use the N example that I've given at the start of the presentation. In the Intel manual, actually what is written is that you'll do a bitwise AND between the 2 operands and store it in the destination. And then the 3 flags are actually set according to a particular, the results of the operation. So there's actually room for kind of like misinterpretation, because sometimes the Intel manual will say that this behavior is undefined. So it depends on the on a particular implementation of the ISA to actually define what the behavior is. So what this kind of like bottom-up approach allow us to do is that we remove all this uncertainty.
Then can this be solved by the Intel provide the more concrete documentation? So if they documents every details of their implementation, then can we just use it?
But you still need someone to convert the semantics into the TAINT propagation rule, because like what I've shown, it doesn't really translate directly. You actually have to understand the subtleties of
what I see from your limitation is that you also have a coverage problem, because you cannot cover all the cases they have designed, right?
Yes.
Okay. Thank you.
Yeah.
Alex Ganfron from Qualcomm. So what do you use for, maybe I missed it, what do you use for your observation engine?
We are actually using Unicorn engine as the observation engine.
So do you rely on them correctly parsing and implementing the semantics of the instructions? Because you need somebody, you need some valid implementation of the semantics to test on, right?
Yes. And because of that, when we are actually verifying the results that we have, we realized that Unicorn engine actually emulates some of the instruction wrongly. So, the details can actually be found in the paper. So yes, I guess this is actually a good thing, because if you're actually running the observation engine on the actual hardware, you get the actual behavior of the hardware.
True.
And
But
this,
then you can't.
yeah,
but then
sorry.
you can't observe the changes. Okay?
Sorry?
But then can you still observe the changes if you're?
Yes, because we can use things like JTAG or debuggers.
All right.
Yeah.
Okay. All right. Thanks.
Thank you.